Hey everyone, today we're going to describe the role of the kidneys in excretion of acid. So acid production can be divided into volatile acids and fixed acids. Your volatile acids are your carbonic acid from CO2, and it's produced by cellular metabolism, and it's anywhere from about 12,000 millimole to 15,000 millimole per day, and you can breathe it off easily through increasing your minute ventilation in your lungs. Then there's fixed acids. There's about approximately 100 millimole per day of fixed acids made. It comes from phosphate, sulfate. But then there's also cellular metabolism through lactate production, and when there's excess lactate, there'll be increased fixed acids as well. We'll focus on fixed acids here because fixed acids are the acids that the kidneys can manage and are able to excrete. There's three fundamental mechanisms for managing acid base in the kidneys. There's secretion of hydrogen ions, reabsorption of filtered bicarb, and then there's production of new bicarbonate. But really, the only physiological way to excrete fixed acids is through the formation of new bicarbonate. So first we'll touch on secretion of hydrogen ions. So in the early segments of the tubules, in the proximal convoluted tubules, excretion of hydrogen ions is secondary active transport. It's in combination with a sodium-potassium ATPase, which pulls sodium out of the cell, which sets up a sodium gradient within the cell for then sodium-hydrogen exchanges on the tubular side to then exchange hydrogen into the tubule and sodium into the cell. In the distal convoluted tubules, there's intercalated cells, specifically the type A intercalated cell, where there's active transport with hydrogen ATPase, pumping hydrogen out with chloride following. This moves into our reabsorption of filtered bicarb mechanisms. So bicarb is filtered out through the glomerulus into the filtrate. About 85% of it is absorbed in the proximal convoluted tubule, 10% in the ascending loop of Henle, and the rest, around 4.9% to 5%, is absorbed in the collecting ducts. You have a little bit of loss that happens, about 0.1% each day. So with our hydrogen that's been filtered out, it will combine with our filtered bicarbonate, make carbonic acid, dissociate into CO2 and water, and the CO2 can easily diffuse across cell membranes, and the reaction happens in the reverse, so you get hydrogen bicarb at the end of the reaction. The bicarb can follow sodium out of the cell, while in our distal convoluted tubules or our intercalated cells, bicarb is exchanged with chloride. Now, with this system, your body pH isn't necessarily changed. The rate of tubular hydrogen secretion per day is about 4,400 milliequimole per day, while the rate of filtered bicarb is about 4,320 milliequimole per day. So you have a slight increase amount, about 80 milliequimole per day of hydrogen ions that are lost, that account for non-volatile acids produced by metabolism. But you have no net gain of bicarb, because bicarb that's reabsorbed is just filtered back out into the filtrate, combines with hydrogen, goes through the same process. So then this brings us to our third point about the production of new bicarb, which is the only way to excrete excess fixed acids. So there's two systems that exist, or there's more, but there's two major ones that exist. So there's phosphate and ammonia buffers in the tubules, and these generate new bicarbonate. So the first buffer I'm going to talk about is the ammonia buffer system, because this is the more important system, or the major system here, that can be upregulated as well in times of acidosis. So glutamine is synthesized in the liver through protein breakdown, carried in the blood to the proximal convoluted tubules, where glutamine is converted to glutamate by glutaminase, and this produces one ammonium that comes off this reaction. And in the proximal convoluted tubule, this can be exchanged into the tubular lumen for sodium. Glutamate can be further broken down into alpha ketoglutarate, and this is through glutamase alpha dehydrogenase. This also produces an ammonium ion, which is then can be excreted into the urine. But the end product of alpha ketoglutarate breakdown is 2-bicarb. So you have 2 ammonium exchanged or made and 2 bicarb made. And the ammonium is bound to a hydrogen ion and is not actively involved in the pH of the tubular lumen or in the cell. So you have a net gain of bicarb, and you can then excrete a hydrogen ion into the tubular lumen. In times of acidosis, the liver can increase glutamine synthesis, which will then mean that you have more breakdown in the proximal convoluted tubules, more ammonium being released, and more bicarb being made. So you have a net generation of bicarb again. This process can increase to a net ammonium excretion of about 500 milliequimol per day. Now, in this process, there's also ammonia that's also generated within the blood from the liver, from other catabolic processes and protein breakdown. Now, ammonia is unionized compared to ammonium. And ammonium has a pKa of about 9.2, meaning that if your pH was at 9.2, so very alkalotic, you would have 50% ammonia and 50% ammonium. But because we're more acidotic, the ammonium becomes locked at its current state, in its ionized state, which means it can't cross cell membranes easily, while ammonia, which is unionized, can cross cell membranes easily and diffuse across concentration gradients. So when you have more acidotic states, you'll have more conversion of ammonia to ammonium within cells, meaning that you'll have less concentration of ammonia within the cell compared to ammonium, which will then drive ammonia to those areas as well. And it's usually quoted that you have about a 1 to 100 ratio of ammonia to ammonium intracellularly. Another aspect of ammonia and ammonium is that they accumulate in the medulla. So ammonium is actively transported into the filtrate in the proximal convoluted tubule, goes down into the loop of Henle, and in acidic conditions, your ammonia will also diffuse across into the filtrate as well, ionize into ammonium and be trapped in the filtrate. Then as it goes to the ascending loop of Henle, it can be actively transported out into the medulla, where it will accumulate and you'll get this medullary cycling. The distal convoluted tubules and proximal collecting ducts are largely impermeable to ammonium, and this serves a really important function because in these areas you have intercalated cells that can actively transport hydrogen ions into the filtrate, into the urine. So as you transport hydrogen ions into the urine in the filtrate, as you'll also remember, most of your bicarbonate has been reabsorbed, so there'll be excess hydrogen ions compared to bicarbonate, which hydrogen ions would want to combine with. So with this excess of hydrogen ions, as they go into the collecting ducts, if there's excess hydrogen ions that need to be buffered, the ammonium that is then transported into the collecting ducts, or the ammonia, will diffuse into the collecting ducts, become ammonium, which then again lowers the concentration of ammonia within the medulla, meaning that it'll follow out of the filtrate or down to that area from high concentration to lower concentration, and then again cycle back into the collecting ducts to then combine with hydrogen to buffer it, becoming ammonium, which traps it through diffusion trapping in the collecting ducts and excreted in urine. So you have net loss of hydrogen ions. So phosphate becomes concentrated within the urine as water is left compared to blood, hence why it's a better buffer in urine than in blood. Phosphate's pKa sits around 6.8. So in normal conditions or normal urine, it's around 50% ionized with a hydrogen ion versus unionized. And then in more acidic conditions, as the urine becomes more acidified, it will buffer more hydrogen ions and become more ionized. So I mentioned before that most of your bicarb has been absorbed by the distal convoluted tubules and collecting ducts. So when there's excess hydrogen ions compared to bicarb, the hydrogen ions will need to be buffered, and they will bind up with phosphate. Because there's less hydrogen ions available within the urine, our Henderson-Hasselbalch equation is pushed more towards the H2O CO2 range. CO2 can diffuse into the cells, liberate more bicarb, hydrogen is pumped out again, you then have a net gain of bicarb into the blood that's absorbed. Lastly, just some points about proximal convoluted tubules versus distal convoluted tubules and collecting ducts. So your proximal convoluted tubules are said to be high capacity, low gradient system, meaning that they can pump out a lot of hydrogen ions, about 5,000 millimole per day, but they can only maintain a gradient of a pH of about 6.7 in the urine. While the distal convoluted tubule and collecting duct are low capacity, meaning they only pump out about 700 millimole per day of hydrogen ions, compared with a high gradient, so they can titrate urine or regulate urine down to about a pH of 4.5, which is the lowest urine can get. But the more acidic the urine is, the more ionized your ammonium is, meaning that it gets trapped in the urine, and the more phosphate will also bind with hydrogen, so the acidity will promote the buffering systems to then liberate more bicarb and excrete more hydrogen ions in urine.